All right, good afternoon, everyone. It's looking to be about that time, so we're going to go ahead and get started today with our additive technology in additive manufacturing breakout section. So my name is Jesse Haworth, and I'll be presenting along with my fellow application engineers, Mark Dolinar and Kanan Irons. We have a lot of stuff for you guys today, and if we have time at the end of our session, we'll be answering some questions, but we're also joined by our moderators, Austin Smith and Brandon Brown, who can answer questions in the Q&A tab as we go along. If you haven't used the Q&A tab in some of our previous sessions, you should be seeing it flashing at the moment with an example question. And before we get into today's content, I'd like to give a special shout out to Markforged for sponsoring this particular session today. You can check them out at their booth in the expo area of our event to chat with them if you have any questions after this session. So for an overview of today, we're first going to briefly cover the overall landscape that is additive manufacturing, which is more or less synonymous with 3D printing. We'll then be going over 3 specific technologies that Hawker Systems is partnered with and what makes them stand apart from other similar technologies. Then we'll go into a bit of a theoretical scenario of being an aftermarket auto parts company and show some examples of what parts we might use our printers for and how they can stand out in that space. And lastly, we'll cover some real-world examples of companies that are using these actual printers to improve their own workflows and internal processes. So to start with, we first want to give a few general categories of how we see most 3D printed parts being used in manufacturing. Now, the first thought that a lot of people have is to straight up replace their final product with a 3D printed version of that. And no one's really wrong for thinking that, since a lot of 3D printed parts are meant for end-use purposes. Now, that being the case, people can get as many or maybe even more benefits from using their printers during the prototyping or manufacturing stages. So for prototyping, as an example, quickly testing things like the fit of a design change or a whole new part can be really, really beneficial, and not having to machine a work holding or create custom inspection fixtures for manufacturing can also help a lot. Now, most of you probably know that there are a lot of 3D printers out there, and we find that they often fall into 3 general categories, with the first one being material extrusion. Now, these are your printers that melt a strand of material layer by layer until your part is complete. These are by far the most common printers, mostly due to their wide range of prices and availability. Then we have the resin printers, which use a vat of material in combination with a laser to create parts. And then lastly, there are the powder-based systems that evenly spread powder in a layer and use a wide combo of different things like agents and heating processes to bind a specific area of that layer into part geometry. We also have a metal category here, which isn't necessarily separate from the actual printing technologies we just mentioned, but we think it kind of deserves its own category in this presentation, since 3D printing metal is really, really unique. So I did mention that we're going to cover some specific technologies today, and here's what we're going to go over. The first one is going to be the industrial X7 system from Markforged, which is a composite machine that can print parts inlaid with continuous fiber. And the most popular is absolutely carbon fiber. Kanan did a great job of covering this in one of our previous sessions, so if you missed that, the recording is available. Then we have the Metal X, which is also from Markforged, but instead of printing plastic or composite, this one prints full metal parts, more or less like the name implies, with the most recently added material being full copper. This uses a process called ATOM, which is atomic diffusion additive manufacturing. And then lastly, we have the HP Multi-Jet Fusion 5200, which is a powder-based machine that is really well known for printing a ton of high quality and strong parts really, really quickly. So the first printer we'll go over is the X7 from Markforged. And for this, I'm going to hand this over to my colleague Mark so he can go over it.
Yeah, thanks, Jesse. So let's actually take a look at Markforged's line of composite printers. These printers pack a really large punch into a very small footprint. In fact, there's actually 2 different lines of Markforged's composite printers. You have their industrial line, and then you have a desktop series that offers very similar capabilities with a smaller footprint and a smaller build area. Now, the reason I really like the Markforged line of 3D printers is it's very easy to actually have one of these printers right next to you in your office. In fact, right now, I actually have one running about 5 feet away from me, building a part as I'm actually presenting in this presentation. So I can actually design, take calls, work on my day-to-day tasks, all while having my parts or prototyped items printed in the background as I watch. Now, Markforged actually has a combination of 2 technologies: fused filament fabrication and continuous fiber fabrication. And Markforged actually has a design philosophy to make it as easy and simple as possible to take your design and then get a part directly out of it. They use a user interface to slice the software called Eiger. Basically, the software allows you to actually upload your files directly to the cloud, and then Eiger will actually slice the file for you, and you can choose whether or not you would like to reinforce it with fiber itself. Finally, you can throw it on the printer and then use it in a very short amount of time. So again, Markforged actually uses a technology called fused filament fabrication. In this technology, you'll actually have a material that's heated up inside of a nozzle, and then the nozzle itself will actually travel around the build bed, placing material only where the model needs material placed at that layer. Now, it's able to do this extremely fast and efficiently. Here's a time lapse of Markforged actually trying to go through and build up the model itself. The other great thing about this printer is any of the support material that's required to actually print the part is actually printed in the exact same material as the part itself, meaning it's very easy to actually peel away the supports once the print has been complete. Now, Markforged itself actually has 3 different base materials to choose from. The first of which is onyx, and many people know onyx. This is a nylon 6 material mixed with chopped carbon fiber. And this gives your parts an extremely great strength to weight ratio. You also have the choice of Onyx FR, which is a fire retardant material. This has a V0 rating, meaning that parts that have a thickness of 3 millimeters or greater are actually self-extinguishing. And then finally, there's a material called nylon white. Nylon white is a non-abrasive option, and it's great for applications like a conveyor belt where you have products moving down the line and may be touching this particular part, and you don't want to mar those parts on the conveyor belt itself. Now, the base materials for Markforged are actually extremely strong in their own sense. You can see it on the flexural stress strain curves right here. But where Markforged really shines is by adding different continuous fibers directly to the part to give it extremely great strength and flexural characteristics. Now, Kanan presented yesterday talking about how you can make parts that are stronger than aluminum parts with a Markforged 3D printer. And you can see on this flexural stress strain curve, you can actually get extremely strong parts directly off of these printers. Now, again, Markforged actually has 4 different filament types. The first of which is fiberglass. And this is a great option if you want to strengthen up your part, but you don't want to add a lot of cost. Carbon fiber is what Markforged is known for. This is what gives you the great strength to weight ratios and what also allows you to make parts that are stronger than aluminum. High strength, high temperature fiberglass is great in those high heat applications where you don't want to have the strength of your part actually deteriorate with heat. This is a great example for like welding fixtures. And then finally, Kevlar is a great option when you have parts that repeatedly see impact. You see Kevlar a lot with bulletproof vests where it's actually able to absorb the impact and then return to its original shape. Now, on this next slide, you'll actually see a screenshot of Eiger. This will actually give you the internal view of the part that's reinforced with either the base material, so in this case, the walls and the infill would have whatever base material you choose, and then the fiber, which is actually routed around the outside and around any of the critical features. Now, you do have the option inside of Eiger to choose where the fiber is going to be placed in order to give your part different strength characteristics. And then finally, let's just take a look at a finished part that was created with this reinforced fiber. In this case, this is a nylon white part. So it's non-abrasive, but by combining it with this carbon fiber reinforcement, you also have an extremely strong part all in one fast and compact package. So Jesse, why don't you tell everyone about the capabilities of the Metal X machine?
Hey, thanks, Mark. So again, if anyone missed the session yesterday about printing strong composite parts, I would really encourage you guys to check it out. One of the examples of just how strong these parts can get was a chain link printed on one of those desktop systems that Mark was talking about that could hold more than 22,000 pounds, which is pretty amazing, all things considered, I would say. But we will continue our Markforged Folks talk by going over the Metal X, which is, again, a 3D metal printer. The printer works in the same way that the X7 does in terms of actually printing the parts, and it runs on the same software too. So we see a lot of customers with Markforged composite experience transition into the Metal X with no problems at all, but vice versa as well. The Metal X has quite a few materials available at the moment, including copper, which was the most recently released, like I mentioned. The materials currently slated to be released next are going to be 316L stainless steel and titanium. Markforged is always trying to keep things as simple as possible, and the really cool thing about how the Metal X works is how straightforward it is to change out material. They're all spool-based, like you can see, just like their plastic counterparts, and when you want to switch to a new material, all you have to do is switch to that spool. There's no hardware swap or anything, and even on the software side, all you really have to do is use a drop-down menu to say what material you're printing with. So Markforged is able to create full metal parts by taking inspiration from metal injection molding and making their spools out of some metal powder that's bound and held together by polymer and wax. Some of this binder needs to be removed from the part before it's fully metal, and this is done by washing the part in a compound that removes that polymer and some of that wax. It's going to sound like a repeat, but this is also straightforward since you can't overwash parts in this solution, and the software tells you how long you can expect to wash them. And so once the parts are washed, it's moved over to a Markforged sintering unit where the remaining metal powder is going to be fused together. And after the part is done sintering, it's fully usable, but you can also post-process it in any way that would be applicable to that base metal. So there are usually going to be three main benefits of using the Markforged solution, and the most obvious one is going to be having hardware in-house that lets users easily print fully metal or strong as metal composite parts with very little hands-on time. If you're prototyping with these systems, you can easily use the saved time to test revisions or improve your product instead of waiting for something like a machine shop to get you your parts. And because you can have such a quick turnaround time on those parts, companies are also able to convert their physical inventory into a digital one. Basically, what this means is that instead of saving a ton of parts in your inventory that you had to build in bulk to save money, you can print a few on demand when you need them. And then the last point is also that you can save your valuable machinist time by sending certain jobs to the printer instead of to the queue of that machinist. This is just another tool in the toolbox, so to speak, and we see a lot of customers benefit from using their current and their new hardware in tandem with each other. So I'm going to hand it off to Kanan Irons now, who's going to go over the 5200 HP MJF solution, and that can offer a ton of advantages as well.
All right, thanks, Jesse, and hey guys. So I'm going to be telling you about the powder-based system example here, and that's the HP Multi-Jet Fusion 5200. And so now this system is a production-grade printing system that enables you to produce thousands of parts that are dimensionally accurate, repeatable, strong, and functional. And if you've ever gone out to a service bureau, an online system to get parts printed, there's a high possibility that they had one of these systems or a previous generation of it. And the reason why is because it's just so fast and it's able to do it at a very good part cost. And you'll see a few pieces of equipment here in the images. The two biggest pieces of equipment are going to be the printer and the post-processing station. And now these two work together through the use of a build unit. And so that build unit is actually mobile. So it's able to move back and forth from the printer to the post-processing station. And what that does is it enables you to separate the cooling portion of your job. And so one requirement with a powder-based system is that after it's been printed, that it requires time to cool. And HP has made an innovation where they've allowed the cooling to be done separately from the printer itself. And so as soon as a print's done, you could load the next build unit into the system and then continue to print. So this saves a ton of time. And then also let's take a look at the materials here. So on the left side of the screen, you'll see the polyamides. Those are your nylon-based materials. But the HP also provides TPU, which is an elastomer or rubber-like material. And they have polypropylene, which is commonly used in injection molding. And One great thing about this production grade system is that it can compete with injection molding for low to mid volume quantities. And that's really changing the game. And another reason that these systems are able to do that is because of something called process control software. So HP has developed this way to ensure that your parts are repeatable and reliable from the first one to the 1,000th one. And it enables you to calibrate your machines based on your environment and in relation to other machines in your facility. And so just to cap it off here, 3 major advantages: speed. So one reason is because that external cooling capabilities, but the other is the way that MJF works itself. So MJF uses a pass-based printing mode rather than a point-based mode. And so most printing systems on the market will have a nozzle or a laser that has to actually touch every piece of geometry in that layer. Well, MJF uses a pass-based method where a print head sweeps across that entire build platform, and it is able to print every piece of geometry simultaneously as it passes over. And so that also really helps with the speed of the print. And then we have part quality and functionality. So parts off this system are strong and durable, yet you can get those really fine details and even internal channels. One great benefit about a powder-based system is that you don't require support to be generated like with other systems. And so if you're looking at doing ducts or internal features, you only have to worry about getting powder out after the printing process is done, because the powder is self-supporting. And then as far as fine details, I've printed parts with walls that are less than 0.5 millimeter thick. And so you can get really fine if you want to. And then last, cost per part. So the material on these systems is recyclable. In fact, it's highly recyclable up to 80%. And so what that means is that if any unused powder from a previous job can be utilized for future jobs. And so at the end of the day, that's going to save you a lot of money because you're getting the most out of the powder in your system. And now let's take a look at how the technology actually works. It's MJF. So MJF is the process of layering powder in 80 micron Z increments. And that's done through a spreader. And then that's followed by the sweeping action of a print head. And in that print head, there are agents or inks that are applied on any areas of part geometry. And then that's followed up with heat from fusing lamps. So take a look at the animation there. We have the spreader followed by the action of the sweeping print head. Another key thing to note here is that we're able to print parts on top of each other, around each other, and we can even print parts inside each other. And that really allows you to maximize the use of that build volume, because again, other technologies are usually constrained to a 2D build platform. And so now we can really maximize how many parts we can get into a single run. And so now that we've told you a little bit about the technology of each one of these systems, we want to take you through a real world scenario, because Jesse, Mark, and I, we're talking to folks all the time about their applications. They're talking about their parts that they've made, and there's always questions that come up, and we help folks answer these questions. And the first one that we're going to look at has to deal with what technology. And so there's so many printing technologies out there, and so we're going to give you some key tips and ideas of how to determine which is best. Next thing we want to look at is going to be, when does it make sense to go to additive manufacturing for your project? Because chances are you've already manufacturing your parts in a traditional way and are wondering, what does it take to move to AM? Then we're going to also take a look at the next one here is how does it compare to traditional manufacturing methods? Because that's key. We want to know how we're becoming more efficient. And then also on the next point here, we're going to look at how it can speed up your workflow. And then finally, at the end of the day, what's the business case? How is it going to save money if I move to this additive manufacturing method? And a lot of the concern here is because we just don't understand the parameters. And that's what we're here to help you with, to really dive into the details and help you understand what would be best. And so what we've done is we've taken the example of an aftermarket auto parts company. When you think in a company like that, you're going to have multiple part designs. You're going to be looking generally at low to mid volume quantities. And you see the example of a Chevy Tahoe here, and Mark and I happen to both drive a Chevy Tahoe. So we're always thinking about ideas of how 3D printed parts can be applied to a vehicle. And we're just scratching the surface with some of these suggestions here, whether it's aerodynamic caps for roof racks, metal brackets, maybe a custom name badge out of metal, maybe a light mount. There's all sorts of areas where additive manufacturing can be applied in this environment. And so what we're going to do now is take a specific part for each technology that we've talked about, and we're going to answer some of those questions from that previous slide. And so to get us started, I'm going to go ahead and pass it back over to Mark.
Yeah, thanks, Gannon. So let's take a look at where Markforged can really shine within a manufacturing environment. So Markforged is great for these one-off manufacturing applications. For instance, things like custom brackets. These require very little lead time with these machines. Simply send it to the machine itself and let it print. One big thing I always like to say is you always have skilled technicians on the floor. Leave them to the harder applications and let the printers do a lot of their work for you. The other thing these additive technologies will do, Markforged, HP, will allow you to actually fail forward. And what I mean by that is a lot of times in design, you might have a general idea of what the part should look like, but you might be unwilling to commit to full production because of the risk of failure and the cost involved. With additive manufacturing, because the per part cost is so low, you could actually try out a part with multiple different revisions, find the one that works best, and then stick with that revision once it's found. Let's take a real-world example of a Markforged part. So in this case, we're actually looking at the engine bay of a 60s Volkswagen bus. And what's common in these buses is to actually take out the old air-cooled engine and place in a modern engine. In this case, this was out of a 2.2-liter Subaru. Now you'll notice that the oil filler neck is actually interfering with the radiator itself. And in this particular picture, they actually cut the oil filler neck in half, rotated the other way, and clamped it on with some rubber hose in order to just make the car drivable so that they can get the testing done. Now, the issue that they were having is they were so backed up working on other projects that there was no way for them to actually build this part in-house. So they were actually looking to, for a job shop to actually build the oil filler cap itself. What they were running into was very high part cost and very long lead time. By switching over to the Markforged, they were able to quickly and easily produce a one-off part. In this case, by going to an outside job shop, they were looking at roughly about $600 for them to machine the top and the bottom of this oil filler neck and then weld it all together. Also, the lead time was at least 2 weeks. Now imagine that when you're working on an old car, if every part has to be custom made and you need to outsource it because you don't have time to actually make it in-house, those custom cars can actually start to become very, very expensive. This is why a lot of these custom one-offs are usually $500,000 for a show car. Well, if we're looking at Markforged as the solution, notice the part only cost about $10, and it took 7 hours to actually print this part, put it on the vehicle, and drive it. The great thing about Markforged is the parts itself are oil resistant, and if you look at this, it looks like a stock component. So it solves two problems at once. It allows them to actually get the car out the door, and it saves them time and money by switching to additive manufacturing for this part. Jesse, what can we do with the Metal X printer?
Hey, thanks, Mark. So for our prototyping example, we'll be focusing on a Tahoe tow hook. You might have saw this highlighted earlier in the graph that we showed. We'll start this particular section off just by showing the finished part first, which is made out of 17.4 stainless steel. And as you can kind of see, this one came looking out great. So up until now, though, we've been talking about the advantages of composite and plastic printing, printing parts stronger than aluminum. So what advantages then does the Metal X provide? Well, the most obvious and straightforward one is that some parts just need to be made out of metal. This can be because of things like extreme temperature or because the part interacts with intense conditions, but some tasks just can't reasonably be done by composites long term. And now again, with an in-house solution that lets you print full metal, you can easily test prototypes like this tow hook for any changes that need to be made, and they're going to perform similarly to the final product. Having to make a small change like a new fillet to design and then sending out that updated part to be machined can really take up a lot of time during the design process, and this can help to shorten those sort of pain points. And even if we take ourselves out of the manufacturing process, one huge advantage of the Metal X is that it can let users recreate parts that are no longer manufactured, or like Mark mentioned, custom one-off parts, and you can modify both as you need. So if, for example, this was a component that the manufacturer no longer made, we could scan or reverse engineer it and change it to fit our own needs before we print it in-house, being made fully out of metal. And by leveraging material swap on the Metal X, you can test different materials quickly to find the best fit for your application. So maybe you want to test a tool steel to see if that's the hardness your part needs, and you can do that real easily. And just like with the composite printers, the Metal X is able to print parts with a sparse infill, which would be literally impossible to machine. We see a lot of applications use metals like aluminum simply for the weight benefits it provides, but with a sparse infill, someone could take advantage of different material properties like hardness while still reducing weight. So for our example here, our printed tow hook was again made out of 17.4 stainless, and comparing it to the original components weight, we see a 37% reduction, which was pretty large. If we needed to, we could leverage this and make the hook out of something like a tool steel though. And so now I'm going to hand it back over to Kanan so he can go over our MJF 5200 example.
All right, so let's take a look at the 5200 example now. So the example that I chose was a roof rack end cap. And so let's take a look at the image here at some of the features. You'll notice that it has a rounded end that will help with aerodynamics, and as well as some side features. We could see some text and a logo on the side, as well as some mounting holes. And requirements for this part would be that it needs to be strong, fully functional. And again, in this scenario of an aftermarket auto parts company, you'd expect low to mid volume quantities, maybe multiple designs for multiple vehicles, makes and models. And in this particular part case, you have a left-hand side and a right-hand side. And so now what I want to do is show you what this would look like in a production scenario for the HP 5200. And then we're going to compare it to an injection molded version. And so this part would be a great candidate for injection molding, although there would need to be some design changes. Specifically with draft is going to be one of the main things. But a great benefit of going with the printed version is I don't have to worry about that. I could print it, I could make it the way it needs to be made for the function and for the cosmetic look of the part. And so let's go ahead and take a look at a production scenario with the 5200. And so on the left side, you're going to see what a typical job would look like with this part. Notice how the parts are nested together, stacked on top of each other, and we're really able to fill up that build volume. In fact, we're able to fit 68 parts in a single run. And one of the key determining factors on part cost when you're looking at MJF is the packing density. How much geometry are you able to fit in that build platform? And so typically you want to be around 8 to 12% for most efficiency. And you could go outside of that a little bit, which I've gone on the high end of that, which is fine. We're still able to get good part costs. And then the other thing that we look at is print time. So start to finish here, we're able to turn this around in under 24 hours. But let's take a look at the breakdown of the print time here. So we have preparation and unpacking at the beginning and end. That's going to be your human labor involvement. That's the involvement in using the nesting software, prepping the build, and unpacking your parts from the post-processing station. And then we have print time and cooling time. And notice the print time is 11 hours and your cooling time is 10 hours. And so with HP, again, the ability to externally cool allows you to continue printing as soon as that print time's done. And so while one job's cooling, you've already started the next one. And here's where it gets really exciting, is to part cost. And so total part cost on a 5200 is about $11.12 a part. And now if you jump up to the upgraded version of the 5200, which is called the 5210 Pro, you can bring that down to $6.08 per part. So now we're in that realm of injection mold cost for low to mid volume quantities. And the main difference between the 5210 Pro and the 5200 is the ability to buy bulk materials, and you're going to have cheaper consumables. So that really allows you to save on part costs, especially if you're doing higher volumes of parts. And so let's go ahead and look at an adjustment on this production schedule. So we're going to look at 1 build per day compared to 2 builds per day. So over the course of a year, let's say you're working 260 days per year, that's 68 parts per day. You're able to get over 17,000 parts in a year. But again, with that external cooling, we're able to jump that up to 2 builds per day because the printing portion was only 11 hours. When we do that, we double it to 136 parts per day. Now we're at over 35,000 parts per year. And so this is the type of thing that you can do with an HP system, specifically because that innovation of external cooling. And now I want to take a look at a chart that compares MJF versus traditional manufacturing. And I'm talking about injection molding. And so I went out and got a quote on this specific part because their part cost in this comparison, it changes based on part geometry and specifically how well that part will pack into the build volume. And so it's good to do this on a case-by-case basis. And so I'm really excited to share this with you because it's on this exact part. And so I have costs for an injection mold in the US. And remember, with molding, you're going to have that upfront cost of machining the mold. And for the US mold, this upfront cost is $17,000. What I've done is bake that into the part cost so that we can get a good one-to-one comparison. Then also have a line showing an injection mold in China. And based on market research, I've found that you could save about 60% on part costs when you go overseas. But there are some other key challenges with going overseas, such as lead time. So there's logistical challenges. And then we have the 5200 and the 5210 Pro. And notice how the curve is flat for MJF. From 1 to thousands, it's going to be the same part cost. And that's not the case with injection molding because you have that tooling cost. And the key areas to look at here are those inflection points. Let's start off with the 5200 versus the US mold. We see that inflection point's about 3,000 parts. And we're purely looking at part costs, not considering any of the other lead times or any other post-processing that might be done. And so that inflection point's at 3,000 units. But when you jump up to a 5210 Pro, that inflection point for the US mold goes up to around 17,000. And so what this should tell you is that MJF is here to stay and it's competitive with injection molding. And the best way to understand this is to reach out to folks like us who are able to give this comparison to you. Because you need to know how well the parts are going to pack, how many you could fit in a build. And those are key things that will help you determine what it's going to look like when you do this comparison. And so going on to the next slide here, we want to look at MJF versus traditional. So the injection molding versus MJF on some key things. Lead time. So injection molding, you're going to get very quick lead time after that tooling has been made. But sometimes that tooling can take months to produce. And this process is optimized for high to mid-volume quantities. And compare that to multi-jet fusion. As soon as your CAD design is complete, you could send that to print and immediately get an in-use part. And so this really allows you to overcome things like supply chain disruption, which we have seen certainly this year. And this process is optimized for low to mid-volume quantities. Now, the next point we want to look at is revisions. What if you want to make a change to your design? And so with injection molding, you could do minor revisions to molds. But any major revisions are going to require a new mold to be made. And that's going to take more time and more upfront hardware costs. And then going to MJF, you can do complete redesigns at no additional manufacturing costs. And so that's key as you're developing your product, you're tuning things in to be just right as you understand the field research and how it's performing out there. Now the next point we want to look at is multiple parts. Let's say you have an assembly, and in this case we have a left hand and a right hand version of the part. So molds must be created for each part that you have. And there's logistical challenges with storing old molds. Let's say you had a part that was created 5 years ago and you might need it again. You have to store that mold somewhere. Whereas with MJF, you can do this digital inventory and print things when you need them. And so you're able to save that space. You don't need a warehouse to store your molds, and you could print it on demand. And with MJF, you could print multiple parts in the same build and even full assemblies that are already assembled to save time. Now the next point we want to look at is design freedom. So with injection molding, there are requirements. There are part design things that you need to consider, such as draft and undercuts, and even features on the sides of parts like we had in this case. That's going to cost more money. So additional cost for complexity in your injection molded parts. Whereas with MJF, complexity is no problem. And so you have an excellent design freedom, and it doesn't cost you any more. And it is advantageous to design your parts so that they pack well, and that's going to bring down your part cost. And so another key feature is that you can have these unique and customized parts at no additional cost. And then part cost, we saw the example there. So injection molding is always going to be great for those really high volume quantities, and MJF is going to be great at the low. But there is an inflection point around the mid-volume quantity range, and it's important to find that inflection point. Like I said, it moves around based on your geometry and how well the parts pack. And so now we're going to take a look at manufacturing aids for our last section, and I'm going to turn it back over to Mark.
Yeah, thank you, Ken. So additive technology is great for those low to mid production runs. As Kanan said, especially when you're getting into those really high productions, injection molding, the cost per part is just so low. But I want to talk about manufacturing aids for just a minute. The reason being, these are excellent for arguably every company. So some companies don't have products that they could produce in an additive method and sell as an end-use part. But every single company needs a manufacturing aid at some point in their life cycle of that product. And additive manufacturing offers some real great benefits for these aids. The first of which is because of additive manufacturing, the part cost can be extremely low, especially if we're running one or two of these units. You don't have to go out to any shop and get a minimum order quantity to get the part cost down. For these manufacturing aids, the first of which is you can just have fixture setups that help to reduce costs in the different stages of the assembly. The other thing that you can look at are machining costs. And for the most part, machining fixtures can be extremely expensive. And if an end mill goes into that fixture, a lot of the times the end mill and the fixture can be destroyed. Now, getting fixtures that are the exact size of the part are very rare. So being able and being flexible enough to print a fixture that holds the part exactly how you like it gives some key advantages. For one, when you're machining, you can take advantage of high-speed machining, and the high speed rate, the high turnover rate of parts, and the low tooling wear that comes with high-speed machining by making sure that your parts are actually fixed to your table properly. So let's take a look at some real-world examples that deal with manufacturing aids. The first of which is from a company, BMI CAD. And what they were looking to do is actually create a bar stock puller. Now, these pullers, the automated versions, can be tens of thousands of dollars. And the problem that lies in is the companies don't have that much capital to actually invest in those automated pullers. Now, you could go through and try and machine this part, but notice this part is extremely simple. And what I always like to tell people, machinists cost a lot of money, and it's well deserved. They're very skilled at what they do. So why not give the hard work to the machinists so that they can make the complicated machining and then take the easy stuff and throw it on a printer? In this case, they actually 3D printed this bar stock puller, and they actually reinforced this with a onyx material and carbon fiber. Now, in this case, they didn't want to actually take the part and put a machine down for a couple of hours to actually machine away this puller. So they were looking at outsourcing it. The problem is the outsourcing and lead time were very expensive. So by taking it in-house and printing it on a Markforged machine, they were able to reduce the cost to about $13, and it only took 8 hours to print. Now they have a bar stock puller, and they can customize this for each one of their applications that they're working on. The other big advantage of this is if you lose this, if you break it, it gets thrown away, it's not a big deal because the total cost is so low. Another great advantage where Markforged really shines is with welding fixtures. And this is a company, SDHQ. They actually make off-roading equipment. Now, what they wound up happening is for a lot of their fixtures, this was a very manual and labor-intensive process. Now, the issue with this is even if you have the most skilled fabricator, there's still variables that you have to account for when you're doing a fixture by hand. First of which is when you're bending the fixtures, there can be imperfect bending. You can have crooked tacking. There's corrosion capabilities on steel parts. It's very hard to repeat the exact same fixture over and over again because of that. And ultimately, there's always human error involved. So by bringing it directly into an additive manufacturing form, you can reduce all of those quality issues and let the printer do its job for you. So by bringing in this fixture, welding fixture in-house, they were able to reduce the amount of time they were taking to make these fixtures, roughly about 156 hours, down to only 12 hours to print these parts directly on their printer. At the end of the day, the total part cost was actually greatly reduced, and they were able to make these welding fixtures for only about $10. The big benefit with this is they didn't have to worry about corrosion anymore, and if they ever need to make an additional fixture, maybe their production starts to ramp up, they can make one that's the exact same size. So their product lines are the exact same, and they don't have to worry about variances between one and the other, making it that much easier to ramp up production. Jesse, what are some examples where Metal X shines in manufacturing?
Yeah, thank you, Mark. So the first customer example I'll go over on the Metal X side of things is Goering, who manufactures custom tools for their customers. So for this particular application, Goering wanted to improve the life of a cutting tool that was used to machine cast aluminum pieces. The original version of their cutter would wear after machining about 10 parts, and their customer needed to machine over 100 parts per month. And so using the Metal X, they were able to increase the number of teeth on the cutter, create an interchangeable teeth system, and then use H13 tool steel as the material to increase the life of every individual tool that they manufactured. And so the second customer example for the Metal X that we'll look at today is Nika Systems and some custom clips that they use with their crucible systems. These systems are meant to melt a wide range of samples in some platinum crucibles to be analyzed later. This meant the material holding their crucibles needed to withstand some very high temperature cycles, so Inconel was going to be a natural fit for this. Now, at first, Nika did try to machine these clips, but the price for outsourcing that machining wasn't exactly what they were looking for. So next, they did try to print these on a metal laser sintering machine as well, but these machines are extremely expensive. So since they couldn't bring that tool in-house, they eventually started to run into the same lead time problems that they saw with machining. This is when they started to look into the Metal X, which was able to print these in-house and then give them the function that they needed. You can see that they also got a lot of quality out of these parts as well. So the picture on the left here has a photo of a Metal X printed clip and one that they received from a metal laser sintering printer. The clip on the left came off the Metal X. So not only did they get a much more direct and affordable solution, but the visual quality was higher as well. And so I'm going to hand it back to Kanan here, who is going to be wrapping us up today with some examples on the HP side of things.
All right. So when it comes to manufacturing aids for multi-jet fusion, the proof's in the pudding, because HP actually uses over 80 manufacturing aids in their production line for these printing systems. And so whether you're looking at assembly fixtures or maybe it's a gasket installation tool, and I even put a couple of color examples from the 500, 580 series MJF machine, which is more of a prototyping machine. But you can see even on the bottom left-hand corner, we have a wire harness assembly fixture. You're able to add colors and text and numbers, and you can even do JPEGs. You could actually put those on the part. And even to QR codes, and also adding color for go, no-go gauges. And I want to go ahead and show you one video of a CMM inspection fixture. And so a CMM machine is a coordinate measuring machine, and that allows you to ensure that your manufactured parts are in spec. But those fixtures are traditionally machined fixtures. And a lot of time you have complex geometries that are a little awkward. This is one great example of how MJF can be utilized. You just put all these in the printer in one job and you have them printed completely and you're good to go. And there are tons of possibilities, but this is just a few to get you thinking about different ways HP can be used for manufacturing aids. And so with that, we're running close to the end of the time here. So let's go ahead and move to the Q&A section. And I did check some of the questions that were being asked. And it looked like we had one question. I'm sure there's a bunch of them in the chat, but I have a question that came in from David here about the powder-based system. And so I could take this one. And so his question was about how powder-based systems handle infill structure. And that's a great question, because if we're thinking about, let's say, the Markforged machine, it will generally generate an infill structure, normally a triangular type structure on the internal geometry. And I'm talking about inside your walls. And so with a powder-based system, if your CAD model is solid on the HP machine, it's going to print as solid. And you also asked about parts being trapped inside, powder being trapped inside parts. That does happen. So let's say you have a box. Inside that box, there could be powder. And we often will recommend that you design little holes so that you can get the powder out, or leave it as is, because the powder is going to be trapped in there. And as long as your part isn't penetrated, it'll be good to go. And so that was a great question. And looking here, it looks like that's all we had. So with that, we're going to go ahead and close the webinar now. And Jesse, Mark, and I will be on standby monitoring the chat. But we just wanted to say thank you guys for coming out and joining us today, and also for joining us this week. We hope this was very beneficial and informative for you. And we hope you'll join us in future webinars. So with that, we'll catch you next time.